So welcome to this web seminar from today. I am the host today. My name is Maurizio Falanga, Director of the International Space Science Institute. And last Thursday, we started with a new series called Habitability from Galactic to Microbial Scales. And the last talk was already last Thursday, but today, I'm happy, especially happy to welcome Tsvi Piran, who will give a talk on the cosmic explosions and galactic life. I will just introduce very briefly Tsvi Piran is the Schwarzmann Chair for Theoretical Physics at the Hebrew University of Jerusalem. He graduated in 76 at the same university and was a research fellow at Oxford, in Austin, and at the Institute for Advanced Study in Princeton. He was at Harvard, Columbia, and New York University, and a distinguished Moore Scholar at Caltech. So he was very prestigious universities. He published over 500 scientific papers, and he's one of the most highly cited astrophysicists. And thank you for accepting and to give this talk today. Piran also won several prizes. The Lagrange prize has been awarded to him, and also a prize from the Israel Prime Minister's office in 2019. So we are all eager to listen to your talk. And before you start, I would like to inform everyone how to ask the question. So the question you can ask at the end, and there are two possibilities: or you raise your hand, and then you can ask the question directly. You will be unmuted, or you just write your question in the chat, and then I will read the questions to Tsvi. So now I'm think we are all already very much looking forward to your talk.
Good afternoon. Thank you very much, Maurizio. It's a pleasure to be here. And as you will see later, this talk is somewhat related to the ISSI. So the talk is about cosmic explosions and galactic life and extinction. We have witnessed in the universe, on Earth, several extinctions, and there is debate on what is exactly their origin and what is possible. And I'll try to argue here that at least one of those was produced by something happened coming from us from the very distant universe. So this is the topic here: cosmic explosions, the role of cosmic explosions in life. They are essential for life, but also the fact that they produce little radiation that might have affected us. So the outline of this talk is the following: the role of stars in promoting life, cosmic explosions, how gamma ray bursts, which I'll call GRBs, destroy life on Earth, how often the threatening GRBs take place, and other places in the galaxy. What happens on Earth, this was before, but what happened in other places in galaxy, and what is the galactic habitable zone. And the last thing is that what about other places in the universe and the relation between this and the anthropic principle. And I have a prediction that I won't be able to read this part of the talk because of lack of time. So how are stars responsible for the origin of life? Stars simply synthesize heavy elements from hydrogen. Stars are factories that take hydrogen and convert it to helium, carbon, oxygen, and silicon and iron, all these heavy elements, which are essential for life on Earth. And this was first shown, the initial idea of nuclear burning was given by Hans Bethe in 37, but later on, Babbage, Fowler, and Hall, and independently Al Cameron have shown how this nuclear synthesis works in star and how this is the dominant process. So stars don't live forever. They have a life cycle and they end. The sun will end in a white dwarf. Other stars end in a supernova and with an explosion, and they are this is more interesting. It is interesting to note that even Shakespeare realized that. He says somewhere he loves you so till the sun will get cold and the stars grow old. What he meant is that this will be forever, but this forever is only something like 5 billion years. So the sun will become cold and a white dwarf, but this is not the topic here. What we are more interested in other stars which grow old and explode. This explosion is a supernova, and the supernova is the way that the stars that produce the heavy elements share them and throw them into the rest of the universe. And what we see here is an example of a supernova explosion. Sorry, something jumped here. What we see here is an example of a supernova explosion. This is a supernova that exploded in 1054, about 1,000 years ago. We see the remnants here, and these remnants are this heavy material which is expanding and producing and providing heavier elements, this material which are essential for life for the universe. Not all materials are produced in supernova. The heaviest materials, gold, uranium, and plutonium, are produced when neutron stars merge, and we have seen in 2017 we have seen such a merger, the gravitational wave, and we've seen other signatures, and this is how heavier elements are produced. Now, supernova are common, and they happen in our neighborhood, and just recently, Zucker and I published this fantastic map of a local bubble, which was produced by about 15 supernova, which exploded around in the vicinity of the Earth. This bubble is about 1,000 light years wide, and it contains within this remnant of the supernova. And this story took place over the last few million years, and it created this bubble. Now, this material from the supernova are spread into space, and they reach Earth. So this is not difficult. This is not an easy task. First, this stardust has to cross the heliosphere to get to the solar bubble, which is produced by the solar wind. Once they cross the heliosphere, they get to the vicinity of the Earth. So this still is a problem to cross the magnetosphere of the Earth, but this is also done. And eventually, this matter settles down on Earth, and it reaches, especially when it gets to the oceans, it reaches the ocean, it falls slowly and produces sediments at the bottom of the ocean. And the sediments, we can measure them, and we can detect them, and this is fantastic work which was done by Anton Wallner as a group, and one of the collaborators there is Michael Paul, a very good friend of mine here from the Hebrew University. And what they discovered is a layer of radioactive iron-60, which was deposited about 2.5 million years ago. Now, this iron-60 has a half-lifetime of 2.6 million years, so it could not have produced very long ago. It must have produced something like few million years before it was deposited. So this means that there was a local supernova that produced so much radioactive material that managed to fall on Earth in the not so distant future from us. But we know from the other evidence that this was not the only one, there were 15 others. This one was the latest one. This is not the only information that we have about material falling and from external sources and falling on Earth. This group by Wallner et al. Also detected plutonium 244, a radioactive plutonium, which is a half-lifetime of 80 million years. And they detected this matter, that this matter is deposited now, but they also detected, but this is now can be compared, the rate of deposited, what was deposited now, for measurement in meteorites in the early solar system. And this measurement was done by Wasserbrook's group at Caltech in the 60s. And you can see here that there is a very big difference between what is deposited now and what is deposited at the very early solar system. Much more was deposited at the early solar system. And what we can conclude from this, that about 80 million years before the solar system formed, there was a neutron star merger in the vicinity of the solar system, not very far from the pre-solar system. And this produced about 1,000 Earth masses of these heavy elements, and they fell on Earth. A question which is almost unrelated to this talk is there life-motivated reason for these heavy materials? I have some answer to that, but I won't have time to discuss it in this talk here. But it's very exciting to me to know that such event was accompanying the formation of the proto-solar nebula. Going back to supernova, the supernova have several signatures. First of all, they're extremely bright in the optical, and they can be seen during daylight even, for if they are in the galaxy, in our galaxy for about a month. And you can see here a picture of a single supernova here, which is compared to the rest of the galaxy. It produces more light or comparable light to the rest of the galaxy. They also produce a short X-ray burst, which I'll discuss later. This is another supernova seen in optical and in X-ray. And they also produce this remnant, which we've shown before. And this remnant produced mostly cosmic rays, but also other broadband electromagnetic radiation over 10,000 of years. So these are the signatures. And from these signatures, the most important for our discussion here is the X-ray and UV, which are produced at the early stage. Now, there is an interesting question. Will the nearest supernova destroy life on Earth? This is such a dramatic explosion producing 10 to the 51 Earths. What will it do to us? And Mel Ruderman was the first who dealt with this question, as far as I know, in '74. And he concluded that the most lethal effect will be destruction of the ozone layer by gamma rays emitted by the supernova. So how does it work? We have the ozone layer, which is above the Earth at 20 to 30 kilometers. The gamma rays or X-ray coming from the supernova will produce, will ionize nitrogen molecules that are in the atmosphere. These nitrogen molecules will join with O, produce combination of NOx, where OX can be 1, 2, or 3. And this NOx is an ozone killer. It interacts with the ozone and kills the ozone and destroys the ozone layer. So this is the process, or more specifically, here I have a simple example, just NO plus O3 goes to NO2 plus O2, so this destroys an ozone. And there are various evidence that Mel Ruderman mentioned in his paper, inside the science paper, about this evidence for this. First, there is comparable, the right concentration of NO and NO2 at the ozone layer is at the right value to keep the ozone layer at the concentration that it is. In the late 60s, there was a rise in the O3 and related to the fact that NO elements, NO molecules, which were produced extensively by nuclear atmospheric tests, decreased, and this decrease enabled when the atomic stopped, led to increase in the rise of the O2, O3 level back to to earlier values. So this is attributed. This is one example. And then a third example is the issue of 11 years modulation of NO in agreement with variation in O3. So there's various evidence for this. So accepting this, so the NO, this process destroyed the ozone layer. Now without the ozone layer, the life which is on Earth will be exposed to the UV radiation coming from the sun, and this will be lethal and killing the advanced life forms if they exist. So this is this was the idea, and there are some suggestion that at least one of the five extinctions that we know, the Ovidian one, was produced by this model. So there was some idea. Later on, the ozone layer builds up, the nitrogen elements decay, and the ozone builds up, and you can start again. The question is how much is too much, or how much is enough? And this was addressed by Melot and al, and by Brian Thomas et al. In 2005. The most extensive research was done by these groups, and they have the following estimated. I'll focus on this one here, that about 1,000 kilojoule per square meter will lead to destruction of 95% of the ozone layer. It is not linear, it's a non-linear process. 10 kilojoule per meter square will destroy 60%. 1,000 kilojoule per meter square would discard 98%. This situation is not so simple because the amount of destruction depends on the direction relative to the rotation axis of the Earth. If it's coming perpendicular to the rotation axis, then all the Earth will be exposed. If it's coming along one of the poles, then only half of the Earth will be exposed. So the question is, how is this process working? We will take this for the rest of the talk. We'll take this 100 kilojoule per square meter as the canonical value, and this can be translated now to astronomical sources. This can be translated to 10 to the 46 ergs at 1 parsec. 1 parsec is more or less the distance of the nearest star from us. So if we have something very, very nearby, then 10 to the 46 ergs are sufficient, or vice versa. If you have only 10 to the 46 ergs, then you have to be very nearby. On the other hand, if you have 10 to the 52 ergs, which is extremely powerful, of course, 6 orders of magnitude more, then you have to go farther, and you can go to a distance of 1 kiloparsec, which is a significant fraction of the galaxy. It's not the full galaxy, but it's a significant fraction of our galaxy. So this is a second, these are two values which I'll use here in the rest of the talk. So what about typical supernova? Typical supernova X-ray emission is too low. And here I thought for a second if I should have a happy smiley or a sad smiley, but of course it's a happy smiley. We don't want to be killed so often, and supernova are quite often. So a typical supernova is producing 10 to the 46 to 10 to the 47 ergs, only 10 to the 46 to 10 to the 47. And with typical distances, this means something like 1 kilojoule per meter squared, about factor of 100 below this lethal dose, which is too low to be significant. This was actually a theoretical estimate, but this was confirmed recently. Oops. This was confirmed in 2008 with observation of this event, and you can see here observation by Alicia Soderberg and al. And this was a supernova at the moment of explosion. This left panel is in X-ray, this right panel is in optical. This was a very nice coincidence. The Swift satellite, which is called the Girls satellite today after Neil Girls, was watching this supernova, which was here in this galaxy. And while it was watching for this supernova, it detected in the same field of view this other supernova exploding in X-ray. And so we have very good estimate of only 2 times 10 to the 46 ergs. So supernova are there, but they are not dangerous. It doesn't mean that they are meaningless. Already in the late 50s, Edward Ney suggested that the long-term supernova have impact, and this impact is by cosmic rays, because the cosmic rays coming from a supernova remnant will now ionize the top of the atmosphere, and this will produce molecules which will catalyze formation of clouds. And if there are more clouds, then the temperature will go down. And this figure is, the credit for this figure is to Nir Shaviv, another colleague from Jerusalem who is working a lot on this process. And indeed, if you remember this supernova that I mentioned, that was 2.5 million years ago, which was discovered using this radioactive iron, this period corresponds to the transition from the Pleistocene to the Pleistocene period, and there was a significant cooling at that time that may suggest that these ideas are working in nature. But what about, but this is not lethal, but so what about this really destruction of life? And here we come to gamma ray bursts. Gamma ray bursts are the brightest explosion that we know. They were discovered accidentally by the Vela satellites. And this was a complete accidental discovery because the Vela satellite were sent not as a scientific satellites, they were sent actually as a spy satellite to detect, to ensure that nobody is doing nuclear explosions in space. There was the first treaty about nuclear explosion which forbade such nuclear explosions. So this satellite were launched by the United States, and they didn't detect nuclear explosion, but what they did detect is some strange explosions coming from outer space, and these are gamma ray bursts, and this was the first gamma ray burst ever detected in July 2nd, 1967. By the way, I didn't mention it, but we must go to space to detect this because the Earth's atmosphere absorbs gamma rays, so we cannot detect gamma ray bursts on the surface of Earth. We have to go above the atmosphere. This is what these satellites do. And we see here that at the moment of explosion, a single gamma ray burst overshine the rest of the gamma ray emission of the whole universe at the same time. So these are really powerful events. And these events are the only events that we know from outside the solar system that directly influence the Earth. And here, there were two cases in which an event like this that happened outside of the solar system. In one case, it was even outside the galaxy. In another case, it was inside the galaxy, and it was powerful enough to shake the atmosphere, to shake the magnetosphere. The Earth's magnetosphere was shaking for a couple of days, for a couple of hours after these two events. The first one was detected in 1983, and another one was detected in 2004, in which we saw such a phenomenon. So this just shows you how bright they are. So how do gamma ray bursts destroy life? We go back to Mel Ruderman's idea by destruction of the ozone layer, and these guys are powerful enough to do this because they emit so much more. They emit about 10 to the 52 ergs, or even more in a powerful event, as I'll show later. And this was first pointed out by Thorset in 1995, and then, as I mentioned, elaborated by Thomas and Melot in 2005 and others. Another idea suggests that this gamma ray burst will produce jets of cosmic rays that may destroy life. This is less likely, so I won't discuss it here. So what about gamma ray bursts? There are four types of gamma ray bursts. They are long, which are associated with the death of massive stars. They are short, that are associated with this merger that I already mentioned before. There are low luminosity ones, which are much more frequent, but much nearer to us because they are frequent, but they're also much weaker. And there are also soft gamma repeaters. The event that I mentioned before that happened in 2004, which shook the Earth's atmosphere, was not a regular gamma ray burst. It is what we call a giant flare from soft gamma repeaters. The peak energy here is 10 to the 46 Hertz, so it is lowest of all of them, but the rate is much, much higher than all the others. So this is where they stand. So this is a comparison of the luminosity function. What we see here is the luminosity on this axis and the rate on this axis. And we see that these are the long gamma ray bursts are the most powerful ones, but the rate is the lowest. And we have the short gamma ray bursts which come from mergers, which are sitting here. And here we have the low luminosity gamma ray bursts, which are even more frequent, but less powerful. And here are regular supernova. And the rate of this SGR mergers is even higher, not by much, than the rate of regular supernova. So this is where we stand. And as I will argue here, that the long gamma ray bursts are the most relevant one for our case, in the sense of being dangerous and possibly destructive. So what you need, what is essential, I don't think we need it, we don't want it, but the limit is about 100 kilojoule per square meter. And this corresponds to 10 to the 52 ergs at 1 kiloparsec, about 3,000 light years, or to 10 to the 46 ergs at 1 parsec. Now the volume goes like, if I relate to be on the same level, the volume goes like e to the 3/2, and the rate will go like e to the minus 3/2. And therefore, if I want to reach this level from a supernova, then the supernova rate has to be 10 to the 6 larger than the rate of long gamma ray bursts, but this is not the case. It is only about 1,000 times larger. And the rate of low luminosity gamma ray bursts in the same argument should be about 10 to the 6 times larger, but it is not. It is only a factor of 1,000 or so larger. And the rest of SGRs, SGRBs has to be 10 to the 9 times larger. So this don't work. And this is the explanation why I said that these ones, because they are so much brighter, are the most relevant one, the long gamma ray bursts. But there is another catch about long gamma ray bursts, is that the rate of gamma ray bursts depend on the metallicity of the galaxy. By the metallicity, we mean as astrophysics by the amount of elements heavier than helium and hydrogen and helium. All these metals that I mentioned before, all this material, not necessarily metals, oxygen and nitrogen and carbon are called metals for this purpose. All these elements which are produced in stars and are polluted, the stars when they explode pollute the galaxy. It turns out that for various reasons, long gamma ray burst happens only in pristine galaxies, whose surrounding has not been polluted. They do happen also in more polluted galaxies, like the Milky Way, but at much lower rate. So this is the relationship between the mass and the metallicity and the rate of gamma ray burst, and the rate of the observed event depends on the metallicity. And here, this is very good news for the Milky Way, because right now, at least, we are quite heavy. This is a fairly large galaxy. There were many stars formed here, many stars exploded, so the galaxy is relatively polluted. And this figure here shows on this side, the metallicity of galaxies with long gamma ray bursts, and on this side, the typical metallicity in the Milky Way. And you see that there are only a small fraction of the gamma ray bursts in such a metallicity. This gives us about a factor of 10 to 20 in the rate. The long gamma ray burst rate in our galaxy is lower by about this factor than the rate of long gamma ray bursts in the universe. And we have to take this into account. As I'll show later in a second, if you don't take this into account, we get a completely wrong result. It's a very important point to remember that so far, we have never seen a single gamma ray burst in our galaxy. all the gamma ray bursts that we saw were from distant galaxies. And as we saw them only in distant galaxies, we have to interpolate and expect from what we know in distant galaxy, what is the rate that these events will happen in the Milky Way. And if we do this interpolation without taking the metallicity factor into account, we may get a wrong result. So this is the this is the estimate that we are doing. And when taking this estimate and taking the consideration of the local density of the Earth, we can estimate here the probability of number of little long gamma ray bursts on Earth within the last gigayear. And we find that the chance is about 20. This is the chance to have the number of long GRBs and of little long GRBs. Little, I mean that it is powerful enough and sufficiently near to cause damage on Earth. And we can do the same calculation for short GRBs, and we see that short GRBs are too weak. There is absolutely no probability, no chance here, but there is more likelihood for significant likelihood for the long GRBs. And we can do the calculation for low luminosity GRBs and for SGR flares, but this is completely irrelevant. So altogether, the chances for extinction on Earth are the following. If we look at what happens in the last half gigayear, and we took at this range of 100 kilojoule per square meter, we see that there is about 50% chance for having one event which was lethal. This is after taking into account the question of metallicity, which causes a lower rate of event in the Milky Way Galaxy. If we didn't take it into account, we would have had a chances of 90%, which is almost certain, but no, the answer is the correct answer is this. And we can also calculate what is the rate per 1 gigayear, but this is less interesting because we didn't have advanced life forms 1 gigayear ago. So the more relevant issue is what happened at about the last 500 gigayears. So this, from this table, this is the relevant factor. And you can see here that if you talk about weaker events, they are very common, and we definitely had weaker events, but they were not powerful enough to most likely to cause such a significant damage. Okay, so this is what happens on Earth. So the answer, to the first question that we asked, is the yes. This is a good chance that this happened on Earth. And I mentioned before that there is a link of this work to ISSI, because this work, which was done with Raul Jimenez, was finished when I was visiting ISSI. And in fact, if you look at the acknowledgement for the paper, you will find that there is an acknowledgement for the Einstein Cafe in Bern, where we finished the last version of the paper. And if I'm not mistaken, we made the point of actually pushing the submit button from this cafe using their Wi-Fi. So this is on Earth, but let's go now to the whole Milky Way. And this is how our Milky Way looks like from the side. And this is how it would have looked if we looked from above. Of course, we couldn't take this picture. This is other galaxies which we believe look similar to the Earth. It has an exponential disk with a scale of about 2.5 kiloparsec, something like 6,000 light years, the scale. And we are 8.5 kiloparsecs, about 30 light years or 25 light years from the center of the Milky Way. And this is very important We are lucky. We could not live here. This is the point of what I will show. What we'll show later. So what happens in the rest of the galaxy? This is a complicated figure of what happens if we go to the rest of the galaxy, and this is the effect of what fraction of the galaxy event destroy, depending on the energy. And we see here that if we have, and we do it for 4 typical places for explosion. 16 kiloparsecs is really the outskirts of the galaxy. 8.5 kiloparsecs is where we are. Somewhere in the suburbs, we are not in the center of the galaxy. We are far from the center. We are a good place in the suburbs. Then 4 and 2.5 are towards are places near the center of the galaxy. What we see here is that there's a powerful event at the center of the galaxy, a very powerful event can influence a large fraction of the galaxy, almost 100%, but a less powerful event will influence less. And now, depending on where you are influencing a larger or smaller fraction of the galaxy. Why is this? Because the mass of the galaxy is concentrated in the center. You remember that I discussed here an exponential disk that is concentrated in the center. So if you explode here, you influence this region, which is very densely populated. On the other hand, if you explode here, you influence only this region, but there is only a small fraction of the are here. So this is why the position of the explosion is important. And these two figures here, these two curves here show the fraction or the relative fraction of such powerful events. So you see there is a small fraction of such powerful events, but when they happen, they do the drastic job and influence large distances. So this shows you here two figures. Basically, what is the fraction of the galaxy which will suffer from a very frequent rate of explosions? And you see that if you are in the center of the galaxy, this is the central region of the galaxy, almost certainly you will have more than one little explosion in your neighborhood within 1 gigayear, and you'll probably have 2 or 3, so it's very difficult to live here in this region. As you go out, it's becoming more and more pleasant, and the chances are less, there is less destruction. And if we are right here where we are, it's about 50% chance of being destructed over 500 million years. And if you go farther out to the outskirts, you're in much better chance to survive. But on the other hand, there are fewer stars here, so there was no much chance to life to build there. So this is what happened, by the way, if we didn't include the metallicity bias, and you see why this metallicity bias is so important in protecting us. So with this, I almost reached the end of this talk, because what we found here is, oops, one slide is missing here, sorry. What we found. So this is my summary slide. So what we have learned here, that this may be a partial, at least, solution to the great silence paradox, to the question of Enrico Fermi, where are they? The gamma ray bursts may simply destroy most of the civilizations in the inner part of the galaxy, which is contain most of the mass of the galaxy. So it is possible that only life can survive only in the outskirts of the galaxy. And since in the outskirts of the galaxy contains much smaller fraction of the mass, this reduces significantly the number of intelligent populations that we can expect in the galaxy, putting a very large damping factor over the Drake formula. Put it differently,
This may explain why we live in such a distant region from the outskirts of the Milky Way, because this is the habitable zone. We couldn't live in a more popular, denser region in the center of the galaxy. Another factor that we know is that the gamma ray bursts are numerous in the past in low metallicity galaxies and the central region of massive galaxies. So life could not form there because of the same reason. And as I mentioned, the habitable zone is the outskirts of large galaxies with high metallicity, in which gamma ray bursts are not common. And last thing, which I didn't have time to discuss here, is about habitability in a more general context. So I was talking about danger of GRBs, gamma ray bursts in our own galaxy. But you have satellite galaxies, which are not far from the Milky Way. And if they are too close to us, a gamma ray burst in a satellite galaxy could destroy life in the Milky Way. And these satellite galaxies are usually small, and they usually have low metallicity. So gamma ray bursts are very prolific there, and they could be very dangerous. Even so, they are smaller in mass. They are very prolific in the total gamma production rate. So what we have to avoid them, we have to live in cosmology which does not let these small galaxies be too close to our Milky Way galaxy. It has to keep them apart. And here, this is one place in which the anthropic principle comes into game. And with this, we can explain with this why the cosmological constant has to be non-zero, because if the cosmological constant was zero, then these galaxies would have been too close to us. But this is a topic for yet another seminar. So thank you.
So thank you so much for your excellent talk. I was very pleased to listen to you, very interesting. So now there are two ways of asking questions, or you raise your hand and then you will be unmuted. So please, if so, start to raise your hand. Otherwise, you can also ask your questions by writing in the chat. We have already some questions in the chat. I will just read them. The first one is from Mark Sargent. It's when assessing the radial velocity of destruction probability within the Milky Way, did you include information on radial metallicity gradients within the galaxy? You find also the question written in the chat.
Yeah, thank you. This is a very good question and a very fine, detailed question. The way we didn't include this information, but what we did include is we did take into account the metallicity of the Milky Way in this figure by just adjusting the rate in the overall rate in the Milky Way to overall rate that we infer of galaxies. A very interesting kind of advanced on this work. This could be done with taking the suggestion of this, including metallicity gradient into account, but we haven't done this.
There's another question from Thomas Redman. The nearly complete removal of ozone will change the stability in the stratosphere. And then essentially, there will be no stratosphere increasing temperature anymore, and the change of the circulation will probably remove NOx rather quickly. Is this included in the calculations?
It's an excellent question. I was not involved in this detailed calculation, but I believe that this whole process is included because the calculation that were done by Thomas and by Melot were including the full atmospheric model. So I'm sure that this was included in this part of the calculation, but this was not my calculation. But the point is that at least initially, for some period of time, the whole ozone layer will disappear. The question is how long it will take to build it up. It's a different question.
I have also a very naive question. You know, now we speak all about these exoplanets and we see the habitability zone of exoplanets, but is, for example, this gamma ray burst, you know, good position to stay far away from them? Is this also taken into account when they speak about habitability? The exoplanet community, let's say.
No, because the exoplanet, when you talk about habitability and planets in the language of the exoplanet community, the question there is only the distance of the star of the planet from the main star, whether it is in the right range for having liquid water. This is the dominant factor, but few other factors are also taken care of into account, and also the type of the star. We don't. The part of the habitability question in this language is the question whether the star does not have huge flares. That if the star has a huge flares by itself, the flares from the local star can do this damage that I'm talking about. So this is not taken into account, but most of the stars that, or maybe even all the stars that are discovered now by search of extrasolar planets are really in the neighborhood of the sun. Because of the difficulty in detection these exoplanets, we are detecting them only from nearby star. And as we are detecting them only from nearby star, they are all from our local neighborhood. So all these planets are more or less in the same position with respect to danger from gamma ray burst. And from all of them, since they are local, they are all in the suburbs, what I call the suburbs of the galaxy. And in suburbia, you're not, it's not dangerous. So you can, so all the stars are not exactly fully protected, but they are not in a great danger of suffering from too numerous GRBs that will hit them.
I see. So someone would like to ask directly a question? There is one question now from William Wall. How widespread are the layers in the Earth's crust with radioactive elements from supernova? Are they found all around the world?
Yes, definitely they are found all around the world. And if I talk about this, it is actually very interesting that there is a refinement of this earlier work by Wallner et al. And they actually have now evidence for not just one, but for two supernova. So this kind of work find evidence for two supernova. One is about, the latest one was about 2.5 million years ago, but there is also evidence for another supernova, which was about 6 million years ago. And this layers is coming from different parts of the world. This is the whole point. And this is not something local. This is not something that could have been produced by some local activity on Earth, but this is something global which came, and the sediments are more or less the same everywhere.
Okay, so I think we can stop here, and I would like, I am sure, in name of all the participants, and especially also in the name of EC. Oh, there is one last question. Let's read the last question and then we stop. So it's Mark Sargent, working, by the way, at EC. Another question, if there is time, okay, let's take it. Do you have a feeling for whatever it is more likely that the potential dangerous long gamma ray burst would have exploded, for example, in the last 0.5 gigayear in the Milky Way or one of its low metallicity satellite galaxies?
Yes, I definitely, for this I have a very good, fairly clear answer. The low metallicity galaxies in the vicinity of the neighborhood of the Milky Way, in particular the Large Magellanic Cloud and the Small Magellanic Cloud, are sufficiently far. They're about 50 kiloparsec from us. And we actually, the nearest supernova that we have seen in the in the recent era, in the 20th century, what happened in one of these clouds, but this was at a distance of 50 kiloparsec away. 50 kiloparsec away is sufficiently far that even if very powerful gamma ray bursts take place there, it won't have a significant effect on us. It will be at most marginal. It will be extremely dramatic event if this happens, but it will be just too far to be lethal. So definitely, with our constellation of the distance, the nearest galaxies, nearest small galaxies, we are fairly safe from them, but local burst in our local neighborhood, even 1 kiloparsec from us could be very unpleasant and could cause some significant destruction.
So, okay, thank you once more. And I would like also to announce the talk for the next Thursday, and it will be within the same topic, and it will be on a cosmic perspective, searching for aliens, finding ourselves. It's given by Professor Tarter, and we are looking very much forward to see you again online and to follow our online seminar. And you have now many thanks from several people listening to you on the chat, and so thank you once more.
Nice to see so many friends. Yeah.
So, bye. Thank you once more. Bye.
Bye. Thank you.
Bye. Thank you.